All right, worksheet 1211, AB number 5, multiple choice pack. We're going to focus on volume, differential equations, some theorems, Johnny, which would be one-dimensional motion, rectilinear motion. So this is a good packet. It has a lot of different stuff. We'll do some of the problems together. I'll generally want you to try them, pause the video, do them together, and then you'll finish the rest on your own. Now, volume of solids or revolution. There's two ways. One, we could slice them like this into disc washers, right? Now, if it's just, so we could use washers. And so the volume it's a circle times the thickness. So it's going to be pi r squared dx or dy. And then minus pi little r squared dx or dy, depending on the orientation of the slices. This is always going to happen, and these are perpendicular to the axis of rotation. So that's your rotation, your axis rotation. That's big R, this little r. And then we're going to integrate it. Now, this right here on its own, that's just a disk, because it doesn't have a hole. A washer is going to be a big disk minus a small disk. The other approach is by using shells. And one shell looks like that, and it has a thickness to it. And these are created by slicing it parallel to the axis of rotation. And they have a radius and a height. Now, if you cut it open, you get a rectangle times the thickness. And the height is still the height, but this dimension up here is going to be the circumference of the shell, 2 pi r. So the volume is going to be 2 pi r h times the thickness dx or dy, and then we're going to integrate it. So that's the approach for shells. Why don't we try just a few of the problems on the front here? We try 1, 4, and 5. Okay. So you could try one, pause it, then unpause it, or you could try all three and then unpause it, then I'll do all three, and then we'll move on to the next page. But go and try these on your own. Number 4, you can use your graphing calculator on. All right. The volume of solid formed by revolving the region bounded by the graph of y equals x minus 3 squared, and the coordinate axes about the x-axis is given by which of the following integrals. So I would draw a picture. This is a parabola that's been shifted right 3 units. That's why we studied all those functions. It kind of looks like that. It says that it's bounded by that and the coordinate axes. So that means this is the region. And then we're spinning it around the x-axis. So that's going to be our other half. And now looking at these answers, multiple choice, you're at the mercy of their answers. So we really do want to do vertical slicing. And that's going to create a disk, right? There's no hole in the middle. So the volume is going to be, and this is your R, the volume is going to be pi r squared dx. The limits are going to be 0 to 3. The radius is going to be y top minus y bottom. Y top, in terms of x, is the parabola, x minus 3 squared dx. And that should be it. So do we see that one there? Pi, looks like A. Oh, shoot. Hold on. Crud. I forgot the extra squared, because that has a squared, so it got me. The other way we could do is we could do shells, and just to show it to you guys, it would be 2 pi r h dy, and then that would be 2 pi, and the limits would be 0 to this value, which would be 9. The radius would be just y, and the height would be x right minus x left. So x right would be the square root of y plus or minus, and then you'd add 3. Now we're going to go with the negative square root of y because it's the left half of the parabola. So it would be 3 minus the square root of y dy. So that would be the shell setup. All right, number 4. Region in the first quadrant enclosed by this graph, and this graph is revolved around the x-axis. What's the volume? It's a graphing calculator problem. So let's try and sketch this. It's in the first quadrant. This is a line, y equals x. And this is a sine curve. So sine curve goes here to 0. And then it's like 2 pi goes like this, right? But there's the amplitude is 2, negative 2. And for sure the sine curve is steeper than the y equals x curve. So you do know it's above it right here. Yeah. Well, you have graphic calculator, so you could verify it if you want. Now we do need this intersection point, and then we're going to revolve it around the x-axis. So that's our other half. We do need this intersection point. So we could graph these. Y equals x, 2 sine x, window 0 to pi, yeah, and then negative 2 to 2. So there's y equals x. There's your sine curve. There's the intersection we need. So this other intersection is 0, 0. I know they both go through 0. So second calculate. Number 5, intersect. First curve, second curve. Guess 1.895494, comma 1.895493. Need extra decimal places. Maybe not that many, but we need extra decimal places, more than 3, before we find our final answer. So now if we do vertical slicing, and I don't think we want to do horizontal slicing because we would have to be doing inverse sine, and we'd have to break it up. I mean, we could do it with a calculator. Vertical slicing, we're going to get, it's perpendicular to the axis of rotation, so it's going to give you a washer. So the volume is going to be pi big R squared dx minus pi little r squared dx. We're going to integrate them. It's going to be 0 to 1.89549343. Now the big radius is right here, and the little radius is right here, and this is y top minus y bottom, and this is also a y top minus y bottom vertical distance. So y top is the sine curve, the 2 sine x, and y bottom is 0 squared dx minus pi 0 to 1.895493. So the little r is just y equals x minus 0 squared dx. So there's our setup. So on the home screen, you do pi math 9 parentheses 2 sine x close squared comma x comma 0 comma 1.8954943 close minus pi math 9 parentheses well, I guess I don't need parentheses. X squared, comma, x, comma, 0, comma, 1.8954943. And we get 6.677 or 6.678. There we go. Okay, number 5. We have a picture given to us. So let's see. The region R is closed by the coordinate axis, and the graph of y equals k. So it's kind of k. I guess is maybe just a number. What is the value of k? We're trying to find it. Is shown below. When the region is revolved around the y-axis, the solid formed has a volume of 8 pi cubic units. So they're telling you the volume, and then you're trying to find the k value to get that volume, which I've given you guys some problems like that before. So the region is right here. This is a parabola. So the coordinates here would be 0, comma 4k, right? This is 2, 0. This is 0, 0. And we're revolving around the y-axis, so the other half looks like this. So we could do vertical slices, and we would get shells. So that'd be volume equals 2 pi r h dx. And our limits would be in the x direction, 0 to 2. The radius would be whatever x value we're at. The height would be the height of that curve, k x minus 2 squared dx. And then we would want to integrate that. So I think we're going to want to try and simplify this. This is going to be x squared minus 4x plus 4. And then we get k x cubed minus kx squared, 4k x squared plus 4kx. I think that's going to be easier to integrate if we. So then the antiderivative is kx to the 4th over 4 minus 4kx to the 3rd over 3 plus 4kx squared over 2. And then we're going to go 0 to 2. Now remember, this is supposed to equal 8 pi. So now we're going to plug limits in. And so we get, now I'm going to divide both sides by 2 pi right now. That'll just make things a little easier. It gives you 4. So then we get 1. So if we plug 2 in here, it's going to be 16 over 4 is 4. So it's going to be 4k minus, that's going to be 8 32 thirds k plus 8k. 0, if you plug 0 in, just make sure it does give you 0. And then we're going to solve this equation. Actually, I think we could probably solve it by hand because this is all just k to the first power. So let's see, we're going to have 12k, and then least common denominator would be 36, so that'd be 4 4 thirds k equals 4, so k equals 3. That worked out pretty nice. Didn't even need a calculator. Alternatively, we could have done disk washers or disks, and that would be pi r squared dy, and that would be 0 to 4k, and the radius would be x right minus x left, so you'd have to solve this for x. So that would be divide by k square root of both sides, plus or minus. It's going to be the minus because it's the left half of the parabola. So x would equal 2 minus the square root of y over k. So that would be your radius, 2 minus the square root of y over k squared dy. Now, we're going to multiply. If you're going to integrate this by hand, you would want to then FOIL this out. That'd be 4 minus 4 square root of y over square root of k. I'd break those up. Plus y over k dy. So then we would get 4y minus 4 square root of k. That would be y to the 3 halves divided by the new exponent multiplied by the reciprocal plus 1 over k y squared over 2, 0 to 4k. And then we're going to set it equal to 8 pi eventually. And I've lost track of my pi, which is not good. So we could divide pi out of both sides. So now you got to plug 4k into these and 0, which yeah. So anyways, we should get the same answer if we do it that way. Okay, go to the next page. Do a little bit of quick notes and try a few problems together. So volume by cross section. So basic idea is you have a base region and it's formed potentially by multiple curves. You say, all right, fx and gx. And then the cross sections are either perpendicular to the x-axis or the y-axis. It makes a difference, okay? So like in this case, we'll just do as an example, we can say, well, they're all, each of the slices are squares. So we're looking for a formula for the cross section of each slice that has a similar shape. All right. And so this is your 2-dimension, and then the thickness, in this case, it'd be dx, is the 3rd dimension that gives you a 3-dimensional answer. R, they often use R, is the base of the solid. So that's what we're building the shape off of. And then if it's perpendicular to the y-axis, it's going to give you a different shape with a different answer. Typical cross sections are squares, so side squared, triangle, maybe equilateral triangles. Because if it's a regular triangle, they'd have to give you more information. Equilateral triangles, the area is root 3 over 4 side squared. We could rederive that. Circles, half circles, 1/2 pi r squared. Sometimes they might do like rectangles, but then they have to tell you like what the height is in relation to the base. So they might say with a height 5 times the base. And so then you'd say, okay, well, my area formula for rectangles, base times height. If the height is 5 times the base, then the height is 5b. And so I get 5b squared, for instance. Why don't you guys try 6 and 8? So pause the video and try 6 and 8. And 6 is a graph and calculator problem. So I'll use graph and calculator to help you on that one. So try those. Pause the video and then unpause it. So let's see. The base of the solid region is closed by. So this is your graph and the coordinate axis. It's a parabola that's been shifted to the right 2. And then, so this is what it looks like roughly. Pictures are very valuable on these. That's your base region. It says every cross section is perpendicular to the x-axis, so these have to be vertical, are squares. So draw one slice. So your volume formula needs to be area in terms of x, which is a square which is side squared. So the volume is now this is 0, 0. This is 2, 0. So we're going to go 0 to 2. Always use the side of the slice that's touching the base region to determine your the sizes of the different parts of the shape. So this would be y top minus y bottom. And so y top is just 3x minus 2 squared. Y bottom is 0. And then you got to square it again. dx. You just put that into your calculator. So we could do math 9. Parentheses 3, parentheses x minus 2, close parentheses squared, comma x, comma 0, comma 2. And there's our answer, 57.600. Okay, number 8. The base of the solid is a region in the first quadrant bounded by this line, which is in weird standard form, the coordinate axes. What is the volume of the solid if every cross-section perpendicular to the x-axis is a semicircle? So I'd probably change this to slope-intercept form first, just so I can graph it easier. So 2y equals 4 minus x. Y equals 2 minus 1/2 x. So that graph is going through 2 and goes down 1 over 2, down 1 over 2. And this is our region. So down 1 over 2, down 1 over 2, this must be 4, or you could do the work to figure out what it is. And the slices are perpendicular to the x-axis, and they're half circles. So the area, their volume, is going to be some area in terms of x dx. They're going to be half circles, which is going to give you 1/2 pi r squared dx. And so I'm going to move the pi over 2 out front. The limits are going to be 0 to 4. The radius is, now this is the radius, so this is the diameter. So the diameter is y top minus y bottom. And the radius is half of that. So we need y top minus y bottom is negative 1/2 x plus 2 divided by 2 before you square it. Now, you could either distribute this 2 into this, or you could square this 2 and bring it out front, which we usually do. In this case, it might not make as much of a difference. But that would be pi over 8 out front. 0 to 4, negative 1/2 x plus 2 squared. Now, if we don't have a calculator, then I think we want to, we could do u substitution, or we could multiply this out. Probably multiply it out, but if you did u substitution, you do this. I don't want the negative 2. So then you get negative 2 out in front. Be u squared du. U cubed over 3. Plug back in the original expression. Plug in the limits, 0 to 4. So it's getting a little tedious. Plug 4 in, that's negative 2, you get 0 cubed minus, if you plug 0 in, you get 2 cubed. So that looks like it goes away. Should come out positive, 8 pi over 12 or 2 pi over 3. 2 pi over 3, A. But you shouldn't get negative answers for area and volume, by the way. If you ever get a negative answer, and clearly something's wrong. Now, if we were to do it with perpendicular y-axis slices, which you shouldn't on this problem, you would get a different answer. But okay. Differential equations. We've been doing a lot of these. So this is just a quick page with a few more review problems on it. So just a review, differential equations are equations that have derivatives in them. So dy dx or y prime. So we deal with these all the time. The major steps are to separate the variables. If you don't do that, you lose all the points. And these are usually worth a lot of points on for response, but you might get them on multiple choice. Integrate each side. That might be worth at least 1 point, maybe 2 points. 3, write the plus c, that's worth a point. If you don't do it, you lose all the rest of the points. Find c using the initial condition, that's another point. 4, solve for y. So that means get y by itself so that you have your particular function. And number 5, the domain. Okay, at least on for response, you got to do domain. Multiple choice, it's, depending. But usually these are tied together as 1 point. So why don't you guys try a few of these? Let's try 10 first, then 11, then 9. We'll kind of go easier to harder. So pause the video, try 10 first, 11 second, and 9 third. And you could unpause it and watch one and then pause it and do the next one and then whatever. But try and practice these yourself. So first step we got to do is separate the variables. Y dy equals x dx. This one's not bad. The integration's pretty easy. It's power rule. Y squared over 2 equals x squared over 2 plus c. You have an initial condition. Now, I like to find the initial condition right now. So the y value is 4. The x value is 3. And so then that's going to be 16 over 4 is 8. Minus 9 halves equals c equals 16 7 halves. And so then our equation is y squared over 2 equals x squared over 2 plus 7 halves. Now, on multiple choice, you generally want to take a look at your picture and see what the answers are. So this one, the answers aren't y by themselves. They're written like this, which kind of looks like, oh, yeah, this is like a hyperbola or something maybe. And so I would use that and say, okay, well, we definitely want to get rid of the 2. And then we probably want the x squared to be positive. I don't know, x squared minus y squared equals negative 7. X squared minus y squared. Okay, so there you go. Okay. Otherwise, if you were to solve and get y by itself, you would then take the square root of both sides, plus or minus. We would go with the positive because when you plug in 3, you should get positive 4. And then you would want to figure out the domain. So the domain would be, well, we definitely want to make sure the inside of the square root is positive or equal to 0. Also, we want y to not equal 0. Well, finding the inside equals 0 is going to be the same thing. So square root of both sides, plus or minus, x equals plus or minus I root 7. Don't need to worry about it. This is always positive. The domain is all reals if you're looking for the domain. Okay, if you haven't, try number 11. Pause the video and try it. Then we'll try it together. Separate the variables with multiplication division. dy and dx need to be in the top. Integrate both sides. Now, don't do natural log right here. You guys love to do natural log. It's power rule. bump it up 1, divide by the new exponent, x squared over 2 plus c. I'd rewrite this negative 1 over y, I think, before I try to do anything else. That's going to be easier. They give you a initial condition. So c equals 1 minus 1 half is negative 3 halves. So negative 1 over y equals x squared over 2 minus 3 halves. And then we got to solve for y. Now, some people might I like that trick where you flip both sides when they're fractions, but you can't just flip. It's got to be single fraction equals single fraction. So you have to combine these as a single fraction before you flip both sides. And then I got rid of the negative by multiplying through by negative. So I think we're looking for negative 2 over x squared plus x squared minus 3. Now the domain of this, just to get practice on it for response, the denominator cannot equal 0. You get division by 0. And there's no issues up here for the derivative, but for the function, x squared equals 3 squared to both sides plus or minus. This has vertical asymptotes at these points. So what I do is I do a number line, and it's a single open interval. So this is different than the domain of this problem. It has this and this and this, but the domain of the solution of a differential equation, single open interval 1, square root of 3 is bigger than 1. So like 1's right there, so that nails down the domain. So the domain for this guy is negative root 3 to positive root 3. Never include the endpoints when doing domain of solution of differential equation. Okay, if you haven't, try number 9, pause the video, and then try it, unpause it, and we'll talk about how to do it. So dy over y equals cosine x dx. We're going to integrate both sides. This is natural log of the absolute value of y. This is going to be sine x plus c. We have initial condition, so we plug that in. And sine of 0 is 0. So c equals natural log of 3. I'm going to rewrite it. Natural log of the absolute value of y equals sine x plus natural log of 3. To get rid of the natural log, we have to exponentiate. Absolute values are still there. Now, rules of exponents say you can break this up into multiplication. People just tend to start to think this isn't in the exponent anymore, or they break it up thinking you could do addition with that. Now that's going to give you a 3. Got to get rid of the absolute values, plus or minus, and people often just forget to do that step, and a lot of times it turns out negative. This time it turns out positive. So this is our solution. And looking at our list, there it is, E. Now the domain, what would the domain be? Are there any values of x we can't plug in sine? No. Any values of x we can't plug in cosine? No. Any values of x or any values you can't raise e to? No. So the domain is all reals. But as interval notation, it'd be negative infinity, positive infinity for free response problems. Okay, you guys are going to do the rest on your own after we try some more problems. So let's go to the next page. And I think I'm just going to do the notes on this page, and then you guys can try the problems. But this is accumulation, exponential growth. So this is this was last stuff that we learned a few weeks ago. So we have rate models, and sort of generically, you might think of a tank that has water coming in and water coming out, and a certain amount of water at any certain time. So the entering rate, we might generically call it E. Unless they give you a name, the leaving rate might generically call L. But if they give you names for those, use those names. The rate model says, okay, well, the amount at any time is the amount at, say, time 0, or whatever time you know, initial condition, plus the accumulation of all the entering water. So this is a rate, so it's measuring change. If we add all the changes up, then we get all the positive changes. And then we subtract all the leaving changes. This is a fundamental theorem of calculus part 1 also, that if you integrate a derivative, you get the change in the thing. A lot of times they ask you for max mins of these, and usually it's appropriate to use extreme value theorem. To find the critical points, you have to take the derivative of this, and you get ET minus LT equals 0 undefined, which you should always write to get full credit on the first one's problems. Now, one of the special cases is that ET equals LT. But I don't want you to jump to that, because then you're kind of skipping some of the calculus. The other kinds of problems that we did near the end were exponential growth. And the definition of exponential growth is that growth rate is proportional to the current population or amount, whatever it is. And that can be written as a derivative. The growth is the change in population over time is proportional to the current amount. Now, if you solve this, you get the population equals the initial population times e to the kt. So I'm going to skip the problems on this page. You guys will go back and do them, but I want to keep going to the next page. We'll do a few on the next page. Next page is the fundamental theorem of calculus part 2. So just a review. So that's when you take the derivative of an integral. Now, often we want to put a different kind of variable on the inside than what's in the limits to be technically correct. So you might see x's out here and t's on the inside. And what it says is that derivatives undo integrals, and then you plug the limits in, top first minus bottom second. But there's one thing that hasn't been taken care of. You got to multiply by the derivative of what's inside, because that's the chain rule. And the derivative of the integral that cancel each other out, well, you still haven't taken the derivative of the limits. So you have to remember to multiply by the derivative of what you plugged inside. So that's part 2. Part 1, just a quick review, is that if you integrate a derivative, they cancel each other out, and you get the original function, and you plug top limit in first and then the bottom limit in second. And we use that a ton. So why don't you guys try 18, 19, and 20? Try 18, 19, and 20. And then, so pause the video, try those problems, and then we'll take a look at them together. So this is the integral of a derivative. So you really should just get what's inside and then plug limits in, right? So you should get 3, 4 squared plus 2 times 4 minus 1 minus 3 times 2 squared plus 2 times 2 minus 1. I mean, that'd be the fastest way to do it. I mean, alternatively, you could take the derivative of this and then integrate it. You'd be doing work and then undoing the work on the very next step. This is 48 plus 8 minus 1. This is 12 plus 4 minus 1. This is 55 minus 15 is 40. So 19. Let f be a differential function. Which of the following are true? If you take the derivative of an integral, you get the original function. Yeah, but then you got to plug the limits in, right? And then you got to multiply by the derivatives of what you plugged in. So the answer ends up becoming 0 for that case. Next one says if you integrate a derivative, you just get the original function. Yeah, but then you got to plug the limits in. So that one's not right. Next one, if I take derivative of an integral, I just get the function. Yeah, sort of. But then you got to multiply. You got to subtract the bottom limit plugged in, and then you got to multiply by the limit of what you plugged in. Now that's going to go away to 0, and so you do get f of x, which is what they said. So 3 is the only one that is true. 20. You got to take the derivative of the integral. You got to plug the limits in. Now be careful. It's going to be sine of x cubed squared. Now I do this for a couple reasons. Minus sine of x squared. Now you got to multiply by the derivative of what you plugged in, not x to the 6th, 3x squared. Not x squared. Don't put a 2x out here. Put a 1. Just what you plugged in, because everything else was taken care of before. So we're looking for 3x squared sine of x to the 6th minus sine of x squared. 3x squared sine x to the 6th. So I think that's the answer C. I think these problems are kind of fun, quick, and easy. Fundamental theorem of calculus part 2. Let's go to the next page. And next page is kind of a mix of a bunch of stuff. A bunch of different theorems and tests. And I'm not gonna write all these down. It's a bunch, but we've been using a lot of these: EVT, extreme value theorem; IVT, intermediate value theorem; MVT, mean value theorem; FDT, first derivative test for relative extrema; SDT, second derivative test for relative extrema. Why don't you guys try problems 22 and 23? So pause the video, try 22 and 23. Then we'll do them together. So 22 says, let f be a differentiable function for all real numbers. The table below gives values of f and its derivative for certain values. Which of the following is true? At x equals 2, the function is increasing. Well, here's x equals 2, and the derivative is positive. So I would say yes, the function's increasing, right? It's not enough to look at the graph and say, oh, the table, it's going up, so it's increasing. And that doesn't matter, because it could be doing a lot of weird things in between that you don't know. But specifically, if the derivative is positive, then it's increasing. There is a relative min in the interval of -1 to 1, but not necessarily at x equals 0. Relative min. So if you look at the values, it actually goes from 0 up to 1 and then down to 0. So that seems like a relative max, right? But that could be a min, because the graph could go up to 5 and up to 4, and this could be a min. Or it could be somewhere else in between. The fact that the slope is going from negative to 0 to positive, let's see, the relative min, I mean, there could be a relative min, right? But is there for sure a relative min? Well, all we know is that it's going down and then it's going up. I'd say for sure there has to be a relative min, because, right? I mean, there might be more, but there's got to be at least one, because this graph is continuous and it's going down and it's going up. Somewhere in there, you have to have at least one relative min. So there's a relative max. I would say you can just see right now that this value is bigger than these, so there has to be a point that's higher than the edges. There has to be a relative max. So we're going to go with all three. Right? 23, table below gives the values of three functions f, g, and h near x equals 0 based on the values given. For which of the functions does it appear that the limit as x approaches 0 is 2? So as we're getting close to 0 from both sides, this one looks like it's going towards 2, right? This one looks like it's going towards 2 on this side, but then there's this jump And so I would say the two sides don't agree. And so I'd say not G. And H looks like it's going towards 2 on both sides, even though it's not equal to 2. That doesn't matter. The limit can exist even if the function doesn't exist or disagrees with it. So I'm going to say F and H based off of what I'm seeing in the table. All right. You can try 25 also. So you can go ahead and pause the video for a second. Try 25. Let f be a differentiable function for f, the graph of f prime. This is graph of the derivative. And then they give you f2 is 10. Which of the following is the best approximate value of f of x? So any value of f of x, what's f of x? F of, I don't know. This is kind of interesting. So they're telling you the value at f of 2. I'm thinking for fundamental theorem of calculus, because we have information with the derivative, but we don't have the function, and we have a point, we want another point. So I would say that if you integrate f prime of x dx from 2 to the x, you're going to get f of x minus f of 2. And that's what we're looking for. So f of x equals f of 2, which is 10, plus the integral of 2 to x of f prime of x. Now, to estimate this, we could just count squares on here. We could say, okay, well, right? And these are going up by 5, by the way. So this is in 1 over here. So this is 5, 5, 5, 5, 5, 5, 5, 5, 5, 5, 5, 5, close to it. So, I don't know. I think if we're looking at this, the graph is going up and up and up and up and up. This is going to be the absolute, this is going to be a relative max right here, right? Because that's a critical point, and the graph is positive increasing to negative decreasing, and over here it's positive increasing. But this is going to be a critical point. This is going to be kind of like a relative min, or at least over here. And this is a relative max, and then the graph starts to go down. So this is going to end up being the absolute max. So if we could just figure out what f of 6 is, I think that would be the safest. So it's going to be 10 plus the area under this curve from 2 to 6. So let's see if we can estimate some of these other kind of, we could say that these together are maybe 5, and these together are 5, and these together are 5, and these together are 5, and this is about 5, and this is at least another 5. So let's see, 10, 20, 30, 40, 50, 60, 70, 80, 95. So I'd say around that. So I'd say it's about 105. So I'm going to go with, what are we trying to find? The maximum value. I'm going to go with E. Seems close because it might be a little higher. I'm going to go with E. Okay, so let's jump to the next page. This is a big packet, but we're getting a lot of it done together. Okay, 20, let's see, Johnny. Did I play Johnny Cash, Walk the Line for you guys? Walk the Line. Okay, so rectilinear motion. We have position, which is typically x, usually on AP test. You have velocity, which is going to be the derivative of x prime. You have acceleration. which is the derivative of velocity, which is the second derivative of position. Some different things that we need to know. Speed is the absolute value of velocity. Displacement is just your overall change in position. So that's the integral of velocity. Anytime you integrate the derivative of something, you get the overall change in what the thing is a derivative of. Now, distance is a special thing for motion, and it's the integral of speed, which is the integral of the absolute value of velocity. We have speeding up, which sometimes they say the speed of the particle is increasing. That means speeding up. Acceleration and velocity need to have the same sign. They have to be working together to speed up. Slowing down, they might use the term speed of particle is decreasing. And acceleration and velocity have to have opposite signs. They got to be working against each other. So, quick little refresher on motion. Why don't you guys try problem 26? Pause the video, try it. Particle moves along the x-axis such a way that its position. So give me a position. What's its acceleration times 0? Well, you got to find x prime, which is velocity. And I guess we're going to probably do quotient rule. Low d high minus high d low all over low squared. Let's see if we can clean it up. -1 minus t minus 1 plus t over 1 plus t squared. T's cancel, so we get -2 over 1 plus t squared. Acceleration, we could do quotient rule again, or we could, I think, avoid it pretty easily by thinking of it like this and say, oh, that's going to be +4, 1 plus t to the -3, right? Which is going to be 4 over 1 plus t cubed. And so then we're going to plug 0 into this. And we get 4. I'm going to let you guys try the next ones on your own, but let's do one more together on the last page. So why don't you guys pause the video and try 31. Okay, and then you guys will do the rest. That'll be the end of the video. Particle moves along the x-axis. They're giving you that. For what values is the velocity of the particle increasing? Now, don't mix this up with speeding up. That would be the speed of the particles increasing. Velocity is increasing means the derivative of whatever you're saying is positive, which means we're looking for positive acceleration. So I think we got to find the acceleration. I think we got to find v first, right? It's going to be x prime. I think we'll just take the derivative of this. We'll use product rule. T plus 1 times 3t minus 1 squared plus t minus 3 cubed times 1. And then acceleration is going to be the derivative of that. So this is getting a little messy. We could just bring the 3 in there. 3t plus 3 times the derivative of this would be 2t minus 3 to the first plus t minus 3 squared times the derivative of this would be 3 plus 3t minus 3 squared Okay, that's pretty ugly. And then we're going to set this equal to 0 and define. We do a line check. But this is a mess. Is there anything we can do before we? I think I don't want to multiply these all out because factoring is the other way. I think we take a t minus 3 out of everything, right? And a 3 out of everything. So if I did that, that would take care of that. That would take out that 3 there. That would take care of that and that. And there'd be a t minus 3 left there and take care of that. And there'd be, okay, so it's going to be t plus 1 times 2 plus t minus 3 plus t minus 3 left over. So I'm just trying to clean this up. So I think we have 3 t minus 3. Here you get 2t plus 2. So we have 4 t's. Plus 2 minus 6 is going to be minus 4. Oh, we're getting close. We take a 4 out of everything. So t equals 3 and t equals 1. Now we're ready for our line check. 1, 3, test, t equals 4, positive, negative, positive. Where's the particle increasing? Now, generally, we do not include negative time. So I'd say 0 to 1, and then 3 to infinity. Now, the velocity is increasing, so we usually include endpoints whenever we say something's increasing. Acceleration we wouldn't include, but since we're saying the velocity is increasing, we include the endpoints. Another way to say this would be that t is between 0 and 1, or t is bigger than 3 or equal to. So, do we see our answer on here? Now, I would say this is the closest, but that includes negative time, but whatever. They're not going to, they're not going to do that on the AP test. They're not going to include negative time. So we'll go with that. That's it. Finish the rest on your own. Check your answers. I'll put the work up later.